Hello everyone, good evening. Welcome to the course of Defects in Crystalline Solids Part 1. This is an 8-week NPTEL course where we'll be understanding about what is crystalline solid, then what are the defects in the crystalline solid and how these defects affect the properties of the crystalline solids. The course coordinator for this course is Professor Sashank Sekhar from IIT Kanpur, and I will be the teaching assistant for this course. The doubts regarding this courses or any other feedbacks or any other questions you have regarding the week's content, you can put it up in the discussion forum or ask me in this live sessions where I will be trying my best to clarify your doubts. If it is not clarified by me, we can always consult Professor Shashank to help us out with the questions. Um, just to give you a brief idea of what we learned in the previous sessions, just to give you a brief idea. Yeah, in the previous sessions, first initially we started our course with the definition of crystallinity. What are crystalline solids? How are crystalline solids different from amorphous solids? Then we went into defects. What are the various types of defects? How are defects present in the material? How, what is the classification of defects on the basis of dimensionality, such as 0D, one-dimensional, two-dimensional, and three-dimensional defects? Then we studied a lot about zero-dimensional defect or point defects. We studied about vacancy, impurity, Frenkel, and Schottky defect. Vacancy and impurity are that kind of defects which are existing in non-ionic solids, whereas Frenkel and Schottky defects are present in ionic solids. The figure here is just to show the different kind of 0 point defects or zero-dimensional defects we studied. Here you can see the interstitial atom, that is a new foreign particle is placed in a material that is known as interstitial atom. Then vacancy, atom is missing from its lattice position. Then substitutional atom, one atom is replaced by a different at the lattice side. One atom is replaced at the lattice side by a different atom. Then substitutional Frenkel pairs. These are all we learned about those. Then we learned about defect reactions, how you can write the different types of defect reactions with the help of Kruger-Wink notation. We also practiced some of the questions on Kruger-Wink notation and how to write it in case of Kruger-Wink notation. So that was just we learned about that. Then we discussed then we discussed about the one-dimensional dislocation, one-dimensional defects. That is, if the point defects spread across a line, they are known as line defects. And the examples of line defects are dislocations, disclinations, and dispirations. We studied about the difference between dislocation and disclination. As you remember, from Volterra model, we got an idea about what dislocation is. It's just we are taking a hollow cylinder and the translation is known as dislocation. And if the hollow cylinder is opened in a angular manner, this is known as disclinations. Then the effect of dislocations is limited to very small region, whereas the effect of disclinations is range to a very high range in the crystal. And generally we studied about this, we study about dislocations because disclinations are not seen in case of metals. Then we introduced the concept of dislocations because we talked about theoretical strength first. Theoretical strength is given by G by 2 pi. G is a shear modulus, is given by G by 2 pi for all the materials. In the case of steel or any other material, when we calculate the theoretical density from this formula, we find that it is very high. The value comes to be very high. But in real life applications or when we do current tests, we do not see such high kind of values in case of steels or any other material. So there is a discrepancy or there is a disparity regarding this, right? Like if the material shows this much behavior, this high behavior according to our theoretical density, sorry, theoretical stress value, theoretical yield stress value, then why is the material in real life not showing that much value? This is where the concept of dislocations comes into play. So if the material has more, like, think what is happening in case of when you apply stress or when you apply tensile stress or a test for the mechanical properties of the material. We are trying to break the bond among the atoms so that the atoms can move with respect to each other. Always a material stays at a very stable state. That means the bond energy associated is quite low in the material. The energy of the system is quite low. Sorry, the bond energy will be high. The energy of the system is quite low. So the bonding between the materials will be very strong. That's why the energy of the system is quite low. Right. So when we need to disturb this stable state, we need to apply more stress on the material. That gives the idea of theoretical density. From that idea, we got the value of theoretical density. But now we say that in real life we don't observe this situation. That means in real life, what is happening? The breaking of bonds between the atoms is easier. That is why we are getting a less value of yield strength or shear strength, right? So why is this less? Because of the presence of dislocations or defects. If there is a presence of defects in a material, the material will easily be able to break the bonds because it is unstable in that portion. It will try to shift those, or the movement will be easy. The movement of the atoms will be easier if there is a vacancy, if there is any other defects in the material. If the movement is easier, if the breaking of bonds is easier, that means the stress will be less. So therefore, in real cases, we observe very less stress or very less strength as compared to the theoretical strength we are observing. The only reason is due to the presence of dislocations. One thing I forgot to say you about we discussed about carburization and fixed laws of diffusion, fixed first law and second law, and how this fixed second law is used in the application of carburization. We learned that in case of point defects. Then coming to the line defects, we learned about various types of line defects. There are two major types of line defects. One is edge dislocations and one is screw dislocations. We understood the difference between edge and screw dislocations. We understood the difference, right? We understood the difference of how what Berger vector and how they are aligned in case of edge and screw dislocations. Let me just show you some videos to make you recall what we learned about edge and screw dislocations. Then we will go into much details for this week's course. Let's watch some videos regarding edge and screw dislocations. Excuse me. This is a video to show you how the edge dislocations looks like or how the edge dislocation happens in the material. As you can see, uh, this is the perfect crystal arrangement in a material. The crystals are perfectly arranged. The crystallinity is well maintained. But what is happening in case of edge dislocations? You see, the atoms are randomly shifting, and there is an extra half plane you can see here, right? There is an extra half plane. This is not bonded, and the bonding between these materials is disturbed. It's not a straight line you can see here. So this is why the real stress of the material is quite less than the theoretical observed value. This is how the edge dislocation looks like from the top view, bottom view it's showing. Then we have another dislocation, that is screw dislocation. This is the video of the screw dislocation. Let me show you. This is the perfect crystal we have. How the screw dislocations looks. See, there is a turning of the atom in a helical path. You can see. This is not a half plane shifting, but in a helical path. See, this is a helical path you are observing. In this way, there is a bond change in the material, as you can see here. This looks like a screw. Therefore, it's known as screw dislocations. So now you got an idea of what is edge and screw dislocation. One more thing to note here is that when there is an atom missing or a plane of atoms missing, or there is an extra half plane inserted or extra half plane created in the material, what is happening? There is bond difference in there is a change in the bonding in the material. The bond strength may be higher, the bond strength may be lower, and this change in the bonding, what is happening? It is creating a stress field around the material. The atoms around these dislocations will be stressed out. Some may have a compressive stress, some may try to occupy the position, compressive stress, or some of them will be trying to get away from it, due to the repulsive forces. So there is a strain field which is developed around these dislocations, because the atoms present around these dislocations are not quite stable. So there will be a strain field around these dislocations. This is what we are going to study today first. And previously we got the value. What did we get? We got the value of stresses. We got the value of stresses. You remember, right? For screw dislocation and edge dislocation, we got the value of stresses. Like, what is the value of sigma? Which we got as sigma is for screw dislocation. For screw dislocation, we got the value of sigma as what we did got the value of sigma minus sigma in case of two axes. One is xz axis and one is zy axis. So in xz axis, the x direction and the z plane, sigma on the x direction and z plane, what we got? Minus gb upon 2 pi sine theta upon r. Then another value we got it for sigma yz, right? Yz is equal to similarly minus gp upon 2 pi cos theta by r. So this shows that the sigma, the stress value is inversely proportional to r. Inversely proportional to r. So if it is inversely proportional to r, if r increases, stress decreases. That's what was the definition of dislocations from the Volterra model. That the effect of dislocations is not felt beyond certain length. If we are increasing the radius of the observation, then the stress will be decreasing. It will not be felt. So this stress is only felt around this dislocation. This shows them that, right? Did you get the point? This is what we discussed. Then then let's see what is happening if the r is very small. Like, what is happening around the dislocation. How does the stress change around the dislocation? How does the strain change around the dislocation? So Professor Shashank used cylindrical coordinate systems. You remember about cylindrical coordinate systems? In cylindrical coordinate systems, in cylindrical coordinate systems, we define everything by r and theta. In cylindrical coordinate systems, we define everything by r and theta. The stress field, the strain field, anything we are discussing, we'll be defining it from the r and theta value. One more point to note here is that when we saw that when r is very high, the sigma value is very small, right? Now let's consider a situation where the r value is less. What will happen? If r tends to 0, sigma tends to infinity. Sigma tends to infinity. Here r tends to 0, right? That means the stress around the dislocation is too high, which is of course expected. Because when we are creating any disturbance within the cell, there will be some areas where the dislocations will be too high. And that is the core of the material. That is the core of the dislocation, not the material. That is the core of the dislocation. That means, as I told you in a, yeah, in case of a edge dislocation, there is arrangement of atoms. For example, this is the arrangement of atoms. What is happening in edge dislocations? There is a creation of an extra plane. There is creation of an extra plane of atoms. This plane is creation of an extra plane of atoms. That means the stress field around this dislocations is quite disturbed. There is a stress field around the dislocation which is quite disturbed. So the dislocation, the effect of dislocation is felt around this material, this area too high. The stress felt around this is too high. Then it will be decreasing when we increase the R as we define from here. Then we define what is like if there is this is the stress field. This is the stress field we are experiencing around the dislocations. Then as we increase the R, the stress field value decreases when we increase the R value according to this formula. That means there is a critical radius below which the stress is extreme, and that is known as the core of the dislocation. That is known as the core of the dislocation. More details you can always refer to Professor Shashank's lectures. I'm just giving you a brief idea which will help you to answer this assignment questions. This time assignment questions are purely mathematical and directly based on the concepts you get. So it's quite easy when you get the understand of the concepts, what is happening around the dislocation. It will be easy to answer these questions. So there is a core of dislocation, right? Around the core of dislocation, or there is particular radius which can define the core of the dislocation. This radius is equal to B to 4B, and the value is taken as 1 nanometers. So around there is a dislocation around a radius of 1 nanometer around the dislocation. In a radius of 1 nanometer around the dislocation, it is known as dislocation core, and there is very high stress in this dislocation core of the dislocation. The energy, see, I am talking about stress, that there is a difference in the bond energy of the material altogether, as I told you earlier. So this energy must be stored somewhere. This extra energy must be stored somewhere. This is stored either in the core of the dislocation or in bigger radiuses when the R increases around the dislocation. And these energies are elastic energies with these are formed due to distortion of nearby crystal planes as they accommodate the dislocations. That means I explained you earlier, there will be disturbances in the bonds around the dislocations, and these disturbances give rise to elastic energy. Elastic energy. Did you get my point? So that means what we discussed, there is an E core where the material where the stress is too high for a material, and this core value is around 1 nanometer around this dislocations, right? We find the value. Then we discussed about edge dislocation, the stress value around edge dislocation, the strain value around edge dislocation. Similarly, we discussed about the edge stress and strain value around the screw dislocations, right? Then we defined some contours, like how these the formulas we got for stress and strain location dislocations, how will they look in the contour? Let me draw some contours here. Okay, point eruption, erasers. Let me rub some of these areas so that we can create space to draw the contours. Yeah. Uh, pen. Yeah. So what are the contours we for edge dislocation? Now we are talking about edge dislocation. Now we are talking about edge dislocation. For edge dislocation, there is a value for sigma xx sigma along the x direction in the x plane, sigma xx value. And according to the when we use the formula, we found that the stress value or the stress value looks like this. Similarly, when we increase the R, it becomes like this. It's quite symmetrical. It's quite symmetrical for x and y, for sigma xx. Similarly, for sigma yy, we observed this value. It's like this. Then there are four values here. There are four small curves here. Sorry, some error. Okay, option eraser. Yeah. So what is happening? Sigma xy. There is a here. Then 1, 2, 3, and 4. This will be of equal lengths. Actually, I'm drawing. That's why it's not in equal lengths. Then this is positive. This is negative. So the opposite ones will be positive. This is positive. This will be positive, and this is negative. This will be negative. The opposite ones will be negative. This is for sigma xy. Sorry, sigma yy. Then we have for sigma xy. How is the contour we are observing? The contour is just opposite to this one. We're getting the bigger circles here, bigger circles here. Then the smaller ones are here. This is what we are getting. And if this is positive, this is negative. The opposite ones will be will be positive, and this will be negative. Right. These are the contours which you are getting for edge stress field around the edge dislocations. And there is one question for regarding this in the assignment, like what is the contour for sigma xy? I think you can get the idea of what is happening around sigma xy. Then this we discussed about the contours of the stress field around that. Then we should discuss about another term called elastic energy. I told you about elastic energy. There will be an energy stored around the dislocation, and that is known as elastic energy. And the elastic energy which is stored around these dislocations, and the elastic energy which is stored around these dislocations is given by the formula E total equals to There are two things here to remember. As I told you earlier, there is a core of the dislocation, which is just 1 nanometer distance around the dislocation, radius around the dislocations. There will be some energy which is stored in the core of the material, and there will be some energy which is stored outside the core of the material, right? And this will be due to the bond difference around the dislocations. So that the total energy will be energy in the core of the material plus energy outside the material, right? Due to the outside or elongation, which is due to the elongation observed. So this value comes out to be alpha g b square. B, you know, as its Burgers vector, G is the stress value, shear stress value, and alpha is a constant which ranges from 0.5 to 1.5. Right? And here you can observe that the core value of energy is less than 10%. The core value of energy is less than 10% as the total value. Total value, core is totally 10%. Then we discussed about Frank's law of diffusion, like how the attractive forces act between or attract association reaction occurs, dissociation reaction occurs, how one Berger vector divides into two due to what reason, and how two Berger vector comes together to save the energy or to lower the energy. This is the points which we discussed about that. Then finally we discussed about energy of the mixed dislocation. There's a direct formula from the energy of the mixed dislocation. You have already seen the values. What is the energy of the dislocation? So now we got the idea about what is the energy of the dislocations, right? Or what is the energy around the dislocations, or how much energy is stored within the dislocation core. Then another point you may say that there are dislocations, they are moving, they may interact with each other. The screw may interact with the edge may interact with screw. Anything can happen. The dislocations will interact with each other. Of course, the dislocations will interact with each other. And these interactions of dislocations, let me just clear my screen. So these interactions of dislocations is defined by two things. One is glide force, one is climb force. So the dislocations can glide with each other, that is motion. By motion they will be gliding among with each other, and they will be climbing with each other. There is a glide, a movement of dislocation occurs by two methods. One is glide and one is climb. More details into this, you can always refer to Professor Shashank's lectures, but I am just giving you an idea of what is happening in glide and in climb. We found the force value, like how the force varies in case of glide and how the force varies in case of climb. Then one more point to note here is that the climb is more thermodynamically expensive process. Thermodynamically expensive process, by what do we mean by that? That means it requires more energy from the outside, because there will be movement of vacancies. Along with that, there will be movement of atoms. If the atoms move in, the vacancies will move out, and if the atoms are moving out, the vacancies will move in. So to create this movement, you require more energy. That is what is happening in climb. But glide, no such extra energy is required for the glide to occur. Then we found the value of what is the line tension, how much force is required to change and everything, how much force is required for glide dislocation, how much force is required to climb for the climb of dislocations. This is what we got about the movement of dislocations. And if there is a movement of dislocations, some of the dislocations may interact with each other, right? This gives rise to the concept of interactions among dislocations. How the edge dislocations, if they are gliding, how they will interact. How the screw dislocations, if they are gliding, how they will interact. And what happens if the screw dislocations interact with the edge dislocations, and how if there are screw dislocations interacting among screw dislocations, what happens if there is edge dislocation interacting among edge dislocation, what happens. So we got very nice curves for those things. You can always refer to Professor Sashank's lectures regarding this, right? Then we understand one more value, that if the dislocations are of the same orientation or same directions, they always try to align with themselves. They always try to align with themselves, right? This is known as low angle grain boundaries. And then when they are of the opposite signs, they will present at 45 degree. They tend to present at 45-degree angle. This is what we are getting from when the it is attaining a lower energy state. If the dislocation wants to attain a lower energy state, then we'll be studying further about these dislocations in later classes. Then another concept is we have of image faces forces. Image forces is, what do you mean by image? Image means there is a mirror image of a material. Mirror image means the same material exists in a different orientation. So how we can extrapolate this into dislocations? What happens? It was generally observed that whenever there is a dislocations on the surface of the material, the dislocation vanishes out from the surface. It never is stable on the surface of the material. So whenever there is a dislocation on the surface of the material, it was assumed that there is a dislocation outside, which is just the mirror image, or there is an image of dislocation, which is uh, if this is the positive dislocation, that will be a negative sign, and the opposite sign. So there is an attractive force between these two, and this will be attracted towards this and will be moving out of the sample. So the dislocations are not present near the free surfaces, never present. So taking this concept into account, when we go into nanoscale range, when we decrease the size of the material, the material will tend to dislocation free material, because the surface dislocations never stay with each other. Due to the image forces, they will be moving out of the system, right? So this shows that when we move into the nanostructured material, the dislocation density decreases. That means according to theoretical strength, what do you remember? The strength will be increasing. The material strength will be increasing because they're dislocation free. So now if the material is reduced to nanometer range, they are more becoming dislocation free. That means they are more tending towards the theoretical density, sorry, not theoretical density, theoretical strength observed. This is what you have learned in this code in this week. Totally, I've just give you a brief idea of what we learned in this week. Now let's solve some of the questions which can help you solve the questions of the assignments. These are the direct questions which are put up in the assignments. Yeah. The existence of distortion around a dislocation implies that a crystal containing a dislocation is not at the lowest energy state. The extra energy of the strain is due to the dislocation. Of course, as I told you, as I mentioned you, what is happening if there is a, let's suppose if there is an edge dislocation, as I showed you in the video, there is an edge. This is a normal crystal where the bonds in the, but if there is an edge dislocation, what is happening? There is a missing atom, or missing plane, missing half plane. So this missing half plane is what is happening. It's creating a bond disturbances around this in the surrounding. There will be a dislocation here, and this dislocation is creating a nuisance or a disturbance in the surrounding atoms. What is this disturbance? This is the existence of distortion. So this statement is true. Of course, the existence of distortion around the dislocation implies that the crystal containing a dislocation is not at its lower, because there is a huge strain field around the dislocation. It is not at its lower energy state. The extra energy is the strain energy due to the dislocation. The extra energy from the lower energy state to the energy state it is in now, there will be a difference, and this extra difference is stored as the strained energy in the material. And the total strain energy, as we discussed, is given by E total equals to core, the energy of the core, and the energy of the due to the elastic strain, that is the energy due to the produced due to the dislocation. So this statement is quite true. Both the statements are quite true, right? Yeah. Then there is a problem in the next question. The shear modulus of a FCC crystal. You remember your FCC crystal structure? The shear modulus of a material of an FCC crystal structure is given. What is the shear modulus of an FCC crystal structure? It's G equals to, so G is given is 50 GPa. And the material is FCC, face centered cubic. And the parameter of the copper, lattice parameter, A value. A is given as 6.2 angstroms. Lattice parameter. What is need to find out? The magnitude of Bircher vector in copper. In case of FCC, what is the value of Bircher vector? Just try to recall what is the value of Bircher vector in case of FCC? Bircher vector value, Bircher vector magnitude is given by, in case of an FCC, A by root 2. In case of an FCC. Similarly, in case of an BCC material, it is given by, in case of an FCC. This is in case of an FCC material. Then in case of a BCC material, it is given by B equals to A into root 3 by 2. B equals to A into root 3 by 2. This is in case of a BCC material. Then we have another, that is simple cubic. In simple cubic, it is given by B equals to A. The magnitude of dislocation is given is same as the lattice parameter. Like you understood what is happening in the lattice parameter is, the Bircher vector is dependent on the lattice parameter. And here what is given is the FCC crystal, right? FCC crystal, that is copper. And for FCC crystal, we will be using Bircher vectors equals to A by root 2. This is in case of an FCC crystal. So that means we will be getting 6.2 by root 2. We will be getting the magnitude of Bircher vectors, right? So what is the magnitude of Bircher vector? We found it. Then there is a question like what is the elastic strain energy per unit length of the dislocation line? Elastic strain energy per unit length of dislocation line. So the elastic strain energy per unit length of dislocation line is given by, what is the value of this elastic strain per dislocation line? You remember I told you in the previous slides. What is the value? GB square, right? Energy, total energy. What is the value of total energy? 2 GB square, right? 2 GB square, right? Or alpha GB square, right? Alpha GB square or 2 GB square. And alpha here it will be 1 because we're talking about only one dislocations. It will be alpha GB square, 1 GB square. And we know the value of G. It is given in the question. And we know the value of magnitude of B. It's given in this question. We found out here. So now we can calculate the energy per energy elastic strain per unit length, right? So we found all the values now and we solved this question. Then we have another question. This is the last question for this session. Then we will be ending the session. Consider two edge dislocations of a given sign. Consider two edge dislocations of a given sign. Yeah. Two edge, so that means the dislocation. What is given here? Two things are given here. The dislocations are of the same sign. means the dislocations, they are of the same sign dislocations. For I'm talking about statement 1 right now. In the C plane, if the dislocations are separated at large distance, the R value is very large. The R value is very large. Then the total elastic energy per unit length is given by, what is elastic energy per unit length? Elastic energy is per unit length is given by G alpha GB square. And if if there are two, what is the there are two edge dislocations. Two edge dislocations means this is for one edge dislocation and there will be another for one edge dislocation. So there are two edge dislocations, but they are far apart. So the interactions between dislocations, two dislocations will be not taken into account. Only their individual elastic energies will be taken into account because they are far apart. The interactions is not present in this dislocations. So adding up these two dislocation, what we will get? We will be getting 2 alpha GB square. So this is true. Then let's consider a case when they are close to each other. Consider two dislocations of the same line and they are close to each other. They are very close to each other. The arrangement can be approximated as a dislocation. So when the materials are when two dislocations of the same sign in the same plane, in the same SIP plane, are very close to each other, there will be interactions among these dislocations. So these dislocations will interact with each other and can be treated as a coupled dislocation, coupled or composite dislocation, because they are interacting with each other. They are discussed as a coupled or composite dislocation. So due to this coupling, the Berger vector value will be 2b. The Berger vector value will be 2b. The combined Berger vector value will be 2b. So this combined effect, the Berger vector value is 2b. Now they have interacted with each other. Now we can consider these interacted dislocations as a single dislocation. So the energy of a single dislocation is given by what? Alpha G B square. But here, due to the interaction among the dislocations, the B value has become 2B. So that will be alpha G 2B whole square, or alpha G 4 alpha GB square. This is true. So now you understand how the dislocations interactions affect the energies, how the dislocations, if they are individually separated with very large distance, affect the energy of the around the dislocation or elastic energy. So finally, you understood everything about what dislocation interaction occurs, how the dislocation movement happens, how there is a dislocation motion such as glide or climb, then how the dislocations interact and how these interactions among the dislocations will affect the energy. Then we studied finally about what? Image forces. Why the material or why the dislocation present, the defect present at the surface of the material never stays in the material. So now you got all the idea about what we are talking about. Yeah. So still, if you have any doubts, this is the end of the session. Still, if you have any doubts regarding this session, feel free to contact me or feel free to put up in the forum so that we can answer your questions. So this was all about today. Thank you so much for attending.